We are going to extend today is essentially the learning dynamics. So till yesterday, we had studied about what is the convergence criterion, what is the saturation behavior of an adversarially trained network. But we had not discussed anything about how that learning dynamics behaves. So today is the discussion around with the learning dynamics. So in what I said over there was, and we are considering an adversarial autoencoder over here. So typically what you have is you have an encoder. You have, I would mention this latent space specifically as a Z over here. You have your decoder. Your input is your X, which goes into it, comes this out. And here you have a prediction of X in terms of X hat. Now, you also have a distribution, which is typically what I would call as P of Z, and from there you can draw samples. You have this one or this one coming into it, then you have a discriminator, and then you do a real versus fake over here. So you have two different losses which go down. One is what you compute between X and X hat, which is J recon, or the reconstruction loss. It's a structural loss. The gradient of that back propagates through both of this network. So you will have nabla J recon going through this, as well as nabla J recon going through this. Now you would have another loss which is getting computed by the discriminator, which is J JD, or the discriminator loss. This JD gets back propagated through the discriminator, I mean the gradient of JD, so that's nabla JD, and then you will have the adversarial loss getting back propagated. So nabla J adversary, which is equal to minus of nabla JD, given the fact that J adversary is equal to 1 minus JD on account of this particular on account of this, you will also be getting this one. Okay, so this is something which we know. Okay. Now that we know that this is going to happen, let's look into what will happen in terms of the loss functions. And that is essentially what we know as the dynamics of learning. So over here, if I look across these epochs, which I can write as K, and here I'm looking at my loss. So I'm using, say, blue, or let me use yellow, the same color, in order to denote J recon. So what you would see is that eventually it would start with a very high loss, and subsequently, as it keeps on learning to be better and better, this would keep on converging. So this is something which you get to see over here. Now, on the other hand, if I'm plotting this J adversary or say J discriminator. So on a J discriminator, initially the discriminator neural network has to learn. So that will also have a high loss. It may be above the reconstruction loss, below the reconstruction loss, or they may not even be on the same scale. And I'm just drawing it to arbitrary scales. So these are all drawn. Let me make a disclaimer. So they are drawn to arbitrary scales. So now I start with a very high loss. The discriminator very quickly try to converge. But then after some time, the encoder part over there will start to learn. As a result of which, while the discriminator is becoming powerful, but this encoder also starting to become powerful, this loss will start to increase. And at a point of time, you would see that this would reach some sort of a saturation. Okay. So this initial phase, let me use a different color. There is this phase of my discriminator. Then I have this phase of my discriminator. And then I have this phase of my discriminator. Now these three phases of my discriminators are pretty interesting. So this is when the discriminator is quickly learning to segregate between real and fake, since their distribution are very different. This is my phase where the discriminator is already trained, but the encoder is now quickly adapting to generate real Z very likely drawn from PZ. Okay, and this is a phase of, this is the end phase. No more updates happening to encoder, decoder, or discriminator. So typically these would be the three phases in which you would see any kind of an adversarial learning working out. Now, it does not mean that it will always be this kind of a very well-defined way. So in some cases you might also see that this can come down, then go up, then down, then up, and then it can have something like this. So something like what you might have seen in So these are typically in RLC circuits when you have underdamped condition, what you see. So it's over here also, it's a very high order nonlinear dynamic system. And since it's a high order nonlinear dynamic system, so you would be seeing these kind of challenges also coming in over here as well. So that's about the dynamics of learning, which you will be observing. But what's critical? Now, just looking at this kind of a curve, you will never be able to really tell whether it's the end phase of learning or not. Okay. So what we do is we also end up plotting the accuracy of this discriminator. So let me use the same colors. This is my J recon. This is my J discriminator. If I'm looking at my adversarial loss, then it will be over here. So, and an adversarial loss follows down opposite of discriminator loss. So it will be low, then it rises, goes to a very high, and then it will come down somewhat over here. So this is my J adversary. Okay. Now, if I'm looking at on this side, I will, sorry. On this side is accuracy of discriminator. So this is 100% and this is 0% is what I'm looking at. So the discriminator initially will have a low accuracy. Okay. Then somewhere over here, it's going to raise to a very high accuracy. And eventually it will come down to this point when it's a 50% accurate part. So that can be a multi-class discriminator as well, or any of them, and you would see that this 50% accuracy of a discriminator is the point when this training has completely ended. So this is typically what you would observe with any kind of an adversarial learning when you are delving into it. So is this clear till this part for all of you before I move to the next part?
Yes, sir.
So now comes another interesting aspect over here. So just give me a second. Give me a minute, I will tell you. So now here we are going to speak about what is the difference between an adversarial autoencoder and a generative adversarial network.
Sir, I have a doubt in the previous graph.
Yeah, please tell me.
Sir, in the phase where the discriminator is already trained, so there we have seen that means when the discriminator is already trained means JD should increase only, means how the training of encoder is affecting the training of discriminator. I am not able to understand that. Means when encoder is already trained, why the loss of JDisk is increasing.
Mm-hmm. So just have a look at this particular plot. So how I start? So say I am looking at the first epoch and there is one sample which is going into it. So I take a sample, I pass it through the encoder, out comes a latent space, I pass that through the decoder over here, then out comes my reconstructed representation of that image. So this is only with one sample in the first epoch. Now what I do is I take this and I calculate my reconstruction loss. So initially none of these are trained, so my reconstruction loss is anticipated to be very high. So based on that reconstruction loss, I find out what is the gradient of that reconstruction loss. And this gradient is backpropagated through the decoder and the encoder. It does not impact the discriminator in any way because the forward pass pipeline was like this. So in the backward pass, it will impact only this one and this one. It does not impact any other network. So is that part clear? Do you agree to it?
Yes. Yes.
Now what I do is that for that particular sample, I had a latent representation Z over here. I know that I want to draw a sample from a certain distribution, which is P of Z. That's my target distribution, which I want to mimic over here. So I draw one random sample from there, one random value just from this distribution. So this can be a 1D distribution. It means there is only one random value getting out from the distribution model, or it can be a random vector which comes out from the distribution model. So if Z is a vector or Z is a tensor in general, then this is a generalized tensor distribution model, as a result of which if I draw a random sample, I will get down a random tensor value which comes over here. So that comes to my discriminator. Now at the discriminator, I have one value which comes from the fake side, one value which comes from the real side, and then the discriminator's job is to discriminate between them. So in the early stage, one point is the discriminator is at random state. It has not yet trained. All the values are random over here. On top of it, the other thing which is there is that this Z and this which is drawn from here, which let me call as Z prime. So Z prime and Z are very different from each other. This one and this one are very different from each other. As a result of which, this JD is going to be very different and very high because these two values are very different from each other. So initially, just with the first epoch and the first sample, your JD is going to be very high. Now, what do you do with this? So this JD can impact this discriminator because this like JD is directly getting impacted from here. So you have this one coming, and that impacts this discriminator. Okay. Now, my target over here is this encoder should update its weight in a way such that this Z looks like as if it's coming from, as if it's Z prime, that is, it's coming from this PZ. Now, the only way, so X is not going to change. It's constant across the dataset. The only way I can modify Z is by modifying the weights of the encoder over here.
Right. Yes, sir.
So if I want to modify the weights of this encoder, how do I aspire to do that? I want to modify the weights of this encoder such that this Z very much looks like Z prime. Now the only way I can do that is if I define a new kind of a loss which is called as an adversarial loss. Now in adversarial loss, what I say is that adversarial loss is sort of like 1 minus discriminator loss. In a sense, if discriminator loss is limited between 0 and 1. Otherwise, if it's limited to some higher range, so whatever is the max value is what will come over here instead of 1. So the purpose over here is that when the discriminator is essentially making minimum errors, that will only be possible when this is very different from this. So what I'm saying is, see, you are not generating this which is very similar to this. So please update yourself very fast. So I want a very high loss going through this one. When this one is very similar to this one, then your discriminator loss is going to be 0. So I will have to send a message back to this encoder. See, this anyways, like you are generating this one which is very closer to this one. So this is making all mistakes. Then you can stop this one. You don't need to update. So that's the rationale for getting this kind of a loss defined. Now, if this is the loss, then I take a derivative over the loss. So my nabla of J adversary is going to be minus of nabla JD, and that's exactly what I get over here. And that is something which I do for updating this encoder. Now, adversarial as a term comes over here because this encoder is sneaking into the performance of this discriminator and is adapting itself so that it can adversarially attack this discriminator into believing that whatever it is sending over here is actually this which is coming from this root.
Yes.
So is this clear to you now?
So, sir, when the discriminator will be trained, at that point of time, the JD will decrease. So that will increase J adversarial.
Yeah.
Okay. But now, if the JD is already decreased, then what is causing JD to increase again? Means how the process should stop
So
there, na?
this is the point. Okay, let me go to the dynamics part of it. So now what is happening over here? So your JD is this one in red. Okay. So initially JD has decreased. How has JD decreased? Because JD has this discriminator has updated itself so that it can discriminate between which is coming from the real versus which is coming from the fake. But at the same time, that JD is also impacting this encoder over here. While this is getting trained, this is also getting updated because of this part.
Yes.
So because that is getting updated, so every time the encoder gets updated, the decoder also needs to be updated, and as simple as that. Now that that is getting updated, so eventually after some time, while your discriminator is not able to train itself anymore, but its error is increasing, and the reason is because this is when the onset of adversarial attack has started. So now the encoder is starting to attack this discriminator adversarially, and that's why you would see that it's starting to make more and more mistakes.
Okay, sir. Yes, I got it.
Excuse me, sir.
Yeah.
Sir, why would J recon decrease with epochs when the weights of encoder is affected because of JD as well, right? So how would we ensure that J recon is going to decrease?
So what happened? So look over here. Come now. So now what happens is, in the first epoch with the first sample, you updated this one. So essentially you updated this one, but after that you got this one and updated only this one. So this is where it will destabilize it a bit. So now in the second epoch or the second sample or second epoch, whenever it goes, so you are again going to update this one. Now this decoder is now getting updated because there was a change in state of the encoder. So after some point in time, while your encoder keeps on getting updated through recon as well as adversary, the decoder will keep on updating itself only with recon, but with the objective that this recon loss is minimized. So it's a gameplay which is happening. So this guy, so it's like this guy is going to attack this one. This guy knows that this guy is going to update itself in order to attack. So that this guy collaborates with this one, he is also going to keep on updating himself. And that is possible by this kind of a dynamic mechanism.
Okay, sir.
See, it's a gameplay. So imagine this one that, so you guys play pranks. So if you are playing prank, playing a prank is sort of a group activity. There are many people who would be the pranksters, and there would be one person on whom the prank is getting played. So the prank is getting played on this discriminator. This guy is the key prankster who is going to prank them. But you would also need a team to support this guy. Otherwise, he will never be able to prank this guy. So this is that team, and this team is going to collaborate with this one so that this is successful. Does that make sense?
Yes, sir. Yes.
And if you are still confused, ask me. I'll try to put down as much as explanation. It takes
Yes,
time
sir.
to really understand this because it's a dynamic system.
So when
So,
JD
like,
is increasing in the when JD is increasing, then at that time our system is misbehaving, right? Because it was supposed, I mean, the attack was supposed to be like that. It should make discriminator believe that Z and Z prime are same, but it is doing the opposite way. So our training should not go beyond that that number of epochs when JD is rising. Means we should stop much before. We should stop before that only. Am I correct if I say this?
So see, if you are stopping your training over here, wait, where is that slide? So if you are stopping your training over here, okay, you need to understand something that your Z is not similar to Z prime. Your objective is to force the Z to behave in a way such that it appears as if it's coming from Z prime, and Z prime is the target distribution which you want to follow. So what you are saying is, okay, all the images of apples should give me a latent space which is similar to as if it's drawn from a Gaussian distribution of zero mean and unity variance. Now, in general, if you don't give a reference to this system of what is a variable drawn from a distribution of zero mean unity variance, then the system will never know. So that reference variable coming from an ideal zero mean unity variance distribution is Z prime. And by way of this one, you are forcing Z to start mimicking itself to the appearance of Z prime.
So so we want Z and Z prime to be different only. So we want JD to increase. Our
No, we
objective.
don't want Z and Z prime to be different. Z and Z prime are different initially. In the final condition, Ari Baba, that the target is, see, my objective is not to make this discriminator powerful. This will happen because it has to be powerful in order to discriminate this. But my objective is that this Z should follow a certain distribution. So let me write it in bold. So the objective is that Z follows PZ. So this is my clear-cut objective. So if my PZ is a zero mean unity variance distribution, then my Z should be a tensor which appears as if it is drawn from a zero mean unity variance system. So I want my Z to follow this system. Initially, it's not going to follow, but at the end point, that is what I want to achieve.
So when JD is minimum, it is following, no? I mean Z is following PZ only when JD is minimum.
No, when JD is minimum, then what is happening? So the loss is minimum, means this is very different from this. If loss is minimum, what would it mean? Then it will always tell, okay, this is the real and this is the fake.
Okay, okay, got it, sir. Got it. Okay.
Only when this and this start becoming very similar to each other, then it will start getting confused.
Right, right. Sir. Yes.
So you are just confusing between accuracy and loss.
Yes, I got it.
Okay, so the next part which I'm going to deal now is on the difference between an adversarial autoencoder and a generative adversarial network. So in case of an adversarial autoencoder, the structure is like this. And the losses which you get down are like this. Given the fact that you have JADV is equal to 1 minus JD. Okay, this is what you get down in case of an adversarial autoencoder. Now, in case of a generative adversarial network, what you get is something like this. So you have a random distribution model over here, which is P of Z. This goes into a generator model over here, and out comes some sort of a X prime. Okay, this I would also call as the Z prime itself, keeping in line with the same thing. Now what you do is you have a database of the real X's. You take this one, you take this one, and you create a discriminator. And then you have the same real versus fake being solved out over here. Okay. Now the losses which you would need is something like this. So when you are doing this one, so your adversarial loss which comes into account over here is then there is another part of it, which is this thing goes into a certain classifier, and this gives you a classification loss. So this part is going to give you a classification loss JC. What you do is you update the classifier by nabla JC. So the objective is that say I want to generate images of horses over here. Then this PZ is a distribution model, which is just 1 minute. Get a classification loss, but you don't update the classifier. Actually, that's a rigid classifier. So I want to generate images of horse. So I will take some random value, I'll pass it through the generator. So a particular distribution model which corresponds to horses. I pass it through the generator. I get this X prime being generated over here, which is an image that I pass through an image classifier. So these image classifiers can be say VGGNet, GoogleNet, AlexNet, any of them. And then you get your output coming from here, which is JC. Now that you have the classifier loss, this classifier loss has to be backpropagated through this generator over here. And remember, this classifier is a rigid classifier. Pre-trained object classifier will not be updated. And then you have your update happening only at the generator side of it. Now the next one is you have your discriminator loss similarly coming JD. This JD is going to update the discriminator with nabla JD. Now on top of it, you again have the same kind of an adversarial loss coming into play. That is going to update itself as nabla J adversary, which is equal to minus nabla JD. And this will update the generator only itself over here. Okay, so this is how a typical GAN model works out. So this is a standard difference between the GAN and the adversarial autoencoder. However, if you look into the learning dynamics, then what you would see is that the reconstruction loss is steadily going down. So this is J recon. Similarly, the classification loss also steadily keeps on going down. This is J classification. The discriminator loss will initially go down and then rise up. Here also it will go down and then rise up. And if I consider the adversarial loss, then the adversarial loss is going up and then coming down over here, which is J adversary. So in both of these cases, you would see that the behavior of this dynamics are pretty much the same. So is this clear to all of you?
So one question. On the GAN network, given the fact that the classifier is a pre-trained network with pretty high accuracy, why is the JC initially for the lower epochs high comparatively?
Because your generator over there is initially having a random state. So I can put random input, but it will not always generate me horses. It has to learn to generate horses.
Okay. Okay.
So the object which it has to, the class of object, the image of an object should look as if it is that object. Otherwise, the errors are anyways high.
Okay.
If I don't update the weights of a classifier, it is of a fixed weight. The only way the error can be high is if the input itself is deviating from what it should be.
Oh, so the classifier is trying to classify horses, but initially, okay, understood. And because x dash is initially random,
yes,
or far away from the ideal horse thing that we want to get, so the losses will be initially be high. Okay.
Yeah.
Thank you. Thank you.
Hello, sir.
Yes.
Yes, sir. So, sir, can we say here that there is a competition going on between our generator and discriminator in GAN and encoder and discriminator between in the autoencoder?
Yes,
right?
exactly.
So, discriminator will try to predict that whether it is real or fake, at fully 100%, and a generator in GAN and encoder will try to put the output such that discriminator cannot say that it is real or fake, right?
Yes, you are correct.
Yes, sir. Yes, sir. Yes, sir.
So there is a competitive game which is being played over here, and the encoder, in case of an adversarial autoencoder, while the generator in case of a GAN is trying to adversarially attack the discriminator to fool it.
So at the end, like at the last graph, you showed that the accuracy like of the discriminator, we want it to be near 50%, so that it doesn't uh, it is like fooled, completely confused, and it doesn't learn either to predict or not to like give the opposite results.
Yeah.
And hello, sir.
Yeah.
So here, like this, sir, what I understand from this 50% logic is that we are like intent to create an such an adverse sorry, sir. We are trying to generate such kind of network in autoencoder or kind of in GAN in generative model, such that this model is so much accurate, like so much creating this fake value or a fake image, or in that case fake Z, such that a discriminator is like 50% like fully confused. 50% accuracy means fully confused.
Yes.
Yes, sir. So like our fake images will be just like real images. So that
Yeah.
discriminator will give like will not be able to discretize this like whether
Yeah.
is it real or fake. So that is why 50% accuracy. Right?
Yes.
Okay, sir.
So one more thing. So the parametric space that we are having here, like how do we will have to decide upon the dimension of it, like, and once we have decided that, so we are saying that these number of parameters, like the number of dimensions, these are the number of parameters required to distinguish like one image, one set from different kind of set.
Yes, so choosing the dimension of Z is a very clever question, and it is more of the designer's prerogative on what should be the size of that Z which you use over here.
So that means we are taking only the essential features and
It depends on
constructing
you
the.
and how you define an essential feature. In most of these cases, say when we are generating numbers or digits, um, uh, even Z as low as 2 dimension is something which works out pretty good.
Sir, that distribution is taken from dataset or we have to define it?
Distribution is your distribution. You are creating a target distribution. So see that this distribution is over Z. This is not a distribution over X. From the data set, you know a distribution model over X, but you don't know a distribution model over Z. Z is something which you can define yourself.
So, sir, it's designer perspective, right?
Yes.
So how to compute, sir, that distribution? This if you want to design.
You don't compute a distribution. What you say is that if I want to generate, say, horses should come from zero mean unity variance. If I want to generate elephants should come from mean of 2 and unity variance. If I want to generate apples should come from mean of 100 and variance of 3. Something of this sort. You can put down your own constraints on it. Just keep something in mind that it's better that they are non-overlapping groups. It's like the amount of overlap between two distributions or area of overlap should be below 5%. That is something which makes a very good condition. So if I want to have below 5%, then the variance, then the mean should be such that the difference between the mean is more than the 6 times sum of variance between these two, or something of that sort. Then you would see that the overlap minimizes significantly.
For each class, sir, we would be required to train separate networks for generating objects
No,
of
no,
the.
no, no, no. You can basically have separate distributions. If you want to extend this GAN to a multi-class, your PZ, there will be different PZ. So PZ1, PZ2, PZ3. Z1 is for your say horses, Z2 is for your elephants, Z3 is for your apples, and then you can have the same network. So based on from where you are drawing a random value, you will be able to generate that kind of an image.
So they will share the same weights, I mean, same network and same weights.
Yeah. See, if I want to create different networks for different pictures, so one is only for elephants, another is only for horses, then I can have the same distribution for elephants, horses, everything. That PZ I don't need to change it. Because the only way I will change it by changing that data set X.
So for such a case, how we will be training it means how we will be providing the input. So we'll provide images of horse one at a time, then followed by elephants. Means how we'll be drawing this.
Yes. So every time you provide image of a horse, then it will be a different PZ. And if when you provide image of a elephant, you will have a different PZ. When you provide image of a ball, you will have a different PZ.
Sir, are we going to do examples on AE and GAN in this course?
So we will give you some tutorial. Tutorial in a sense, like you will have to do it. We'll give you an assignment. So they are coming down. So tomorrow you have the quiz and worksheet, which is lined up for on something to do with vector convolution. So the worksheet is on vector convolution as much as you will actually have to solve. No more parameter calculating business, but this time is like you will have to find out the value at certain locations. We'll give you that worksheet. And for the quiz, it's a mix of all of this. And there will be an assignment, a coding assignment, which is a takeaway assignment. You solve it and then you need to upload the IPython notebooks. And that will have to do on semantic segmentation, and that will also have something to do on the generative model as well.
Sir, what will be the grading distribution for the end-sem offline exam? Will be there end-sem offline exam?
It's already on the website. Just look at it. I don't recall. But whatever is that proportion of distributions, that is the same.
Oh, okay.
Sir, other than tomorrow's quiz and worksheet, we don't have anything other in this month, right? Next month only we have offline exam. After that.
No, there will be. So I think next week Professor Sudeshna Sarkar will start her part on recurrent neural networks and natural language processing. She will also be taking some internal assessment, some worksheets and quiz on that as well. Worksheet, quiz, and I think coding as well.
So, sir, we schedule for that quiz and all. She will provide.
Madam will tell you next week when we start. Madam will tell you.
Okay, sir. Because that's the last day also I was trying to tell you, like, I have to plan my journey. I'm from Rajasthan, sir, so it will take 2 days for me. So I want to book ticket right now. Like I won't get after.
What we will try to do is that because you have been asked to come back by 31st, we will not try to put any more things before 31st.
Yes, sir. So and I'm coming in last week, and many are there. So if you can tell, then we can.
That's the reason I will discuss with Madam because you guys are coming back by 31st. We have the first week of April, which is available to us.
Yes, sir. That is fine, sir. That is fine.
So the next assignments will be in that first week of April only.
Thank you, sir.
Hello, sir. Sir, both of these models are trying to do the same thing. So why different approaches?
Because two people thought that they can do in different approaches, and it does not restrict only to two different approaches. There can be numerous approaches.
So can you give examples in which kind of task GAN specifically works better than AAA?
They are pretty equivocal. My experience has been you can solve it either of them. I have a general preference of going with adversarial autoencoders than GANs. That's it. It's again a preferential thing. Maybe because I started all of this business with AE, that's the reason. I've been doing adversarial autoencoders before GANs were even invented. So,
Okay.
and I started all of this deep learning with autoencoders, and it was natural for me to go with adversarially trained denoising sparse autoencoders.
Yes, yes.
But otherwise, I mean, by now I have realized that they do the same thing. I mean, there is no major difference. Okay, it's already 10 o'clock. Let's close for the day now. And then all the best for the upcoming quiz and worksheet tomorrow.
Thank you.
Thank you.
Thank you, sir.